Welcome to this explainer. Today, we're diving into an absolute engineering marvel that most of us completely take for granted, the evolution of railway signaling and control. We're going to trace this incredible journey from the heavy, back-breaking mechanical levers of the 19th century all the way to the invisible, data-driven networks that manage thousands of high-speed trains today. It's a fascinating progression, so let's jump right in. Here's what we're looking at today. We'll cover the foundation of railway control, dive into the mechanics of mechanical signaling, explore the limits of physical control, and then shift gears to the evolution to electrical interlocking before finally wrapping up with the shift to data-driven systems. Part 1. The foundation of railway control, safety, and capacity. Think about it. Trains are massive, incredibly heavy machines. They travel at insanely high speeds, and, well, they can't exactly swerve to avoid hitting each other. You have to keep them safely apart while simultaneously moving as many of them as efficiently as possible. So railway control is this perpetual, massive balancing act. Every single time engineers achieve a leap in safety and capacity, that exact solution introduces a brand new technical limitation. Keep this in the back of your mind as we go. Part 2. Mechanics of mechanical signaling, a 19th century marvel. To really wrap our heads around this, I want you to imagine a world entirely before modern electricity. Back in the mid-1800s, running a vast rail network relied on pure, raw physical muscle. The operator standing in a traditional signal box was literally the engine powering the whole system. These setups were extremely labor-intensive. It required real, sweat-inducing physical effort from the operator to manually flip the switches on the tracks outside. Let's break down how that physical functionality actually worked. First, the signaler yanks a massive physical lever. Next, that force travels out of the cabin, transferring through a long network of connected galvanized steel rods or tensioned wires running right alongside the tracks. Finally, that direct physical link moves the track points or raises a heavy semaphore arm. It's a direct one-to-one mechanical connection. Now, you might be wondering, what if the signaler just messed up? What if they pulled the wrong lever and sent two trains on a collision course? Well, safety is maintained through something completely ingenious called mechanical interlocking. Right underneath the floor is an arrangement of flat metal bars that physically clash and lock into place to prevent conflicting lever movements. Human error is literally blocked by solid iron. It's fail-safe logic, but built entirely out of metal. Part 3. The limits of physical control, when systems break down. As brilliant as that mechanical interlocking was, it hit a hard physical wall. The control area is strictly limited by the physical distance those rods can reliably move equipment. For track points, that limit is typically restricted to around 320 meters. Imagine trying to reliably push a giant steel switch 3 football fields away using nothing but metal rods and elbow grease. Friction, temperature expansion, and sheer gravity just made it impossible to push any further. So we have a strict geographical leash. If you needed to control a sprawling junction, you had to build multiple signal boxes, hire multiple operators, and coordinate all of them just to get a single train safely through a complex area. To build faster, higher capacity networks, engineers desperately had to figure out a way to break that 320-meter physical barrier. Part 4. Evolution to electrical interlocking, expanding the reach. The big game changer, electricity. Signaling systems have evolved from physical mechanical links all the way to data-driven in-cab displays, with each generation offering different trade-offs in efficiency and reach. In the 1930s, we shifted away from manipulating heavy iron and moved to all-electric relays, fundamentally decoupling the safety logic from human muscle. Enter the fail-safe electrical relay. This unassuming little device completely replaced those massive clashing metal bars under the floor. The safety logic was now executed by simply opening and closing electrical circuits. And the absolute best part? If a circuit failed or lost power, gravity caused the contacts to drop, instantly failing safe and turning all the signals to red. It kept the mechanical safety but completely removed the grueling physical constraints. The ripple effects of this were just massive. Because operators didn't need to provide the raw physical power anymore, those back-breaking levers were swapped out for miniature ones and eventually just buttons on a desk. Heavy rods outside were replaced by electrical cables connected to motorized points. This also allowed for the widespread use of bright, electrically powered color light signals. Suddenly, the geographical reach of a single operator vastly expanded. Part 5. The shift to data-driven systems, the digital railway. Fast forward to today, and the contrast is absolutely staggering.
We've gone from sweat-stained lever frames to sleek, climate-controlled rooms with multi-monitor workstations. The operation of a modern railway relies on a systematic integration of signaling, telecommunications, and control equipment. Each type of technology offers specific functionality designed to enhance safety and capacity, yet each also faces inherent physical or technical limitations. The fail-safe logic is still there, but the interface is totally digital. Instead of relays, we now use computer-based interlockings, or CBIs, where microprocessors crunch the safety logic. We have continuous train detection via data links, and we're even shifting to data-driven in-cab displays. This literally removes the need for physical signals on the side of the tracks. The movement instructions are beamed straight to the train's computer, allowing trains to safely run much closer together and dramatically boosting the network's capacity.
But let's circle back to that foundational idea we talked about at the beginning. Every leap in safety and capacity introduces a new technical limitation. We've gained this incredible network capacity and completely eliminated the physical labor of the 19th century. But it begs the question, what is the hidden cost of relying so heavily on computer processors, software updates, and telecommunication data links? I'll leave you with this to chew on. In our drive for ultimate efficiency, have our modern, highly automated digital railways opened themselves up to entirely new vulnerabilities, like cyber threats? Have we traded the heavy, undeniable, unhackable reliability of clashing iron bars for the invisible, interconnected risks of the digital age? It's a pretty fascinating trade-off, and something engineers are actively wrestling with today. Thanks for joining me for this explainer.